There is something deeply strange about the fact that you are aging right now, sitting wherever you are, reading this, and the reason you are aging, the reason time is moving forward for you at all, has almost nothing to do with clocks or calendars or the spinning of the Earth. It has to do with the shape of space itself. And I want to tell you about that because when you really understand it, not just the words, but the actual picture of what is happening, it changes how you see everything. Now, most people, when they hear the word gravity, they think of things falling. An apple comes off a tree and it goes down. Simple enough. Newton looked at that and said, there must be a force, a pulling force, something that reaches out from the earth and grabs the apple and yanks it toward the ground. And that was a spectacular idea. It worked. For 200 years it worked so well that nobody questioned it. You could predict where cannonballs would land, where planets would be, the whole business. Newton's gravity was a force that acted at a distance, and even Newton himself found that deeply uncomfortable. He wrote in his letters that he could not believe that one body could act upon another at a distance through a vacuum without some medium. He thought it was absurd. But the equations were so good that people just ignored the absurdity and kept using them. Then along comes Einstein, and Einstein does something that is, I think, one of the most beautiful intellectual moves in the history of human thought. He says, wait a minute, what if gravity is not a force at all? What if there is no pulling, no reaching across empty space? What if the Earth is not grabbing the apple? What if the apple is simply following the most natural path available to it through a space that has been curved by the presence of the Earth? The apple is not being pulled down. The apple is falling, because falling is the straightest path through bent geometry. That is general relativity in one paragraph, and I want you to sit with that for a moment before we go further. Now here is where time enters the picture, and this is the part that most people get told but do not actually understand. When Einstein worked out his equations, he was not just describing curved space, he was describing curved spacetime. And that word, spacetime, is not just a fancy way of saying space and time together. It is saying something much more radical. It is saying that space and time are not separate things. They are woven together into a single four-dimensional fabric. And what gravity does is curve that fabric, not just the spatial part of it, but the time part of it too. Let me give you the picture that I think makes this real. Imagine you are a two-dimensional creature living on the surface of a rubber sheet. You can move left and right, forward and backward, but you have no concept of up or down. Now someone places a bowling ball on the rubber sheet, and the sheet sinks down in the middle, curves inward around the bowling ball. If you, the two-dimensional creature, try to walk in a straight line near the bowling ball, you cannot. The geometry of the surface forces you to curve around it. You think you are walking straight, because straight is defined by the surface you live on, but an observer from outside watching you would say, no, that creature is curving. That creature is being deflected by the shape of the surface. That is exactly what happens to light passing near the sun. The light thinks it is going straight because in curved space-time, the straightest possible path is what we call a geodesic, and near massive objects, those geodesics curve. We have measured this. We took photographs of stars during a solar eclipse, and we could see stars that should have been hidden behind the sun because their light was bending around it. The geometry is real. This is not a metaphor. But now here is the thing about time, and this is what I really want you to get. It is not just space that curves near a massive object. The time dimension curves too. And what does it mean for time to curve? It means that time itself runs at different rates depending on how deep you are in a gravitational field. At the surface of the Earth, time runs a little slower than it does high up in orbit, not by much, not by anything you would notice in daily life, but by a measurable amount. We have measured it. We have put atomic clocks on airplanes and flown them around, and compared them to atomic clocks on the ground, and the clocks do not agree. The clocks at higher altitude, further from the Earth, run slightly faster. The clocks at lower altitude, closer to the Earth, run slightly slower. Gravity slows time. This is not a theory anymore. It is a measured experimental fact, and it is so real that the GPS satellites in your phone have to correct for it constantly, or your navigation would drift by miles every day. Now I want to explain why this happens, because just saying gravity slows time is not satisfying. I want the picture. Here's the way I think about it. In space-time, everything is always moving. Even if you are sitting perfectly still in space, you are moving through time. You are traveling through the time dimension at a constant rate, which we might as well call the speed of light, because in a sense, everything in space-time is always moving at the speed of light, just in different directions through the four-dimensional fabric. When you are sitting still in space, all of your motion through space-time is directed along the time axis. You are moving through time at maximum rate. Now, when you start moving through space, some of that motion through space-time gets redirected into the spatial directions, so you move a little slower through time. This is time dilation due to velocity, and it is the basis of special relativity, which came before general relativity and is a little easier to grasp. General relativity adds something to this picture. Near a massive object, the space-time geometry is not flat, it is curved. And the way it is curved, specifically, is that the time dimension gets stretched in a particular direction. Being deeper in a gravitational well, being closer to the massive object, means you are in a region where the time axis is tilted relative to the time axis far away. Your geodesic, your natural free-fall path through space-time curves because the geometry curves. And the consequence of that tilting of the time axis is that you age more slowly, your clocks tick more slowly, your atoms vibrate more slowly relative to someone far away from the gravitational source. Now let me try to make this even more tangible with an analogy. Think about a river. The river is space-time, and you are a boat floating in it. If the river is perfectly flat and calm, you just drift along at a constant rate, and time passes at its normal rate. Now imagine the river starts flowing faster in certain regions because the riverbed is sloped downward, because there is a gravitational well pulling the water downhill. In those regions, the current is faster, but faster in what direction? Downward, toward the massive object. A boat in a fast current is being carried along more in the spatial direction, downward toward the mass, and so it has less of its motion available for the time direction. It ages more slowly. That is a rough analogy, but I think it captures the spirit of what is happening geometrically. Here is the thing that really gets me about all of this, though, and I want to be honest with you about the parts that are genuinely mysterious and the parts we actually understand. We understand the mathematics of general relativity with extraordinary precision. Einstein gave us equations, the Einstein field equations, and they are beautiful. They relate the curvature of space-time on one side to the distribution of mass and energy on the other side. Mass and energy tells space-time how to curve, and space-time tells mass and energy how to move. That is the whole story in one sentence. And those equations make predictions that have been verified to astonishing accuracy. Gravitational waves, the ripples in space-time caused by merging black holes and neutron stars, we have detected those. The existence of black holes, regions where space-time curves so severely that not even light can escape, we have photographed the shadow of one. The precession of Mercury's orbit, which Newton's gravity could not quite explain, general relativity gets it exactly right. The theory works. But here is what we do not understand, and I think it is important to be honest about this. We do not understand why gravity curves space-time. The equations tell us that it does, and they tell us how it does it, but they do not tell us the mechanism underneath. What is space-time made of that it can be curved at all? Why does mass cause curvature? In electromagnetism, we can say, okay, charges create electric fields, and we have a pretty good quantum theory of that. Photons carrying the electromagnetic force, the whole quantum electrodynamics picture, which I worked on for a long time, and which works beautifully, but gravity resists that treatment. Every attempt to build a quantum theory of gravity runs into terrible mathematical problems, infinities that cannot be renormalized, conceptual conflicts between the smooth curved geometry of general relativity and the fundamentally probabilistic lumpy nature of quantum mechanics. We do not have a working quantum theory of gravity. That is a genuine open problem, one of the deepest open problems in physics. So when you ask why gravity creates time, the honest answer is that we know it does. We know how to calculate what it does. We have an incredibly precise geometric description of the relationship, but we do not know the ultimate why in any deep sense. And I find that exciting rather than troubling. It means there is still something profound to discover. Now let me take you somewhere even stranger, because the relationship between gravity and time gets weirder the more extreme the gravitational field becomes. Near a black hole, the time dilation becomes enormous. If you were to hover just outside the event horizon of a black hole, which would require an enormous amount of thrust to stay in place against the inward pull of the geometry, time for you would be passing enormously slowly relative to someone far away. A year for you might be millions of years for your distant friend. And if you were to fall through the event horizon, which from your perspective would happen in a finite time, the outside universe would, in a sense, have run through its entire future in that moment. Now I want to be careful here because the full picture is subtle and the coordinates get complicated, and there are things that are genuinely not fully resolved in how we interpret the physics near and inside event horizons, particularly when you start thinking about quantum mechanics near black holes, which leads to Hawking radiation and the information paradox, which is a whole other rabbit hole. But the basic point stands. Time is not a fixed universal background against which events happen. Time is part of the physical fabric of the universe. It is influenced by mass and energy and the geometry of space-time, and in extreme conditions, it can do things that our everyday intuition finds completely bizarre. Let me say something about why I think this matters philosophically, not just physically. For most of human history, we thought of time as absolute. Newton explicitly assumed it. He wrote about absolute, true, and mathematical time, which flows uniformly without relation to anything external. That is an incredibly deep assumption. It means that there is some cosmic clock somewhere ticking away at the same rate everywhere in the universe, and we are all synchronized to it. Einstein showed that this assumption is simply wrong. There is no universal clock. There is no absolute simultaneity. Whether two events happen at the same time depends on where you are and how fast you are moving and how deep you are in a gravitational well. Time is local. Time is personal. Your clock and my clock can disagree, and neither of us is wrong. This has implications that go beyond physics into questions about the nature of reality and causality and even free will, though I am cautious about going too far down that road because physics is hard enough without adding philosophy on top of it. But I will say this. The picture that physics gives us of time is so different from our everyday experience of it that it demands that we be humble about our intuitions. We evolved on the surface of a planet in a relatively weak gravitational field, moving at speeds much less than the speed of light. Our intuitions about time were shaped by that environment. They work fine for everyday purposes, but they are wrong in a deep sense when applied to the universe as a whole, and any honest engagement with what physics is telling us has to grapple with that. Now, some people hear all of this and they get uncomfortable. They want to know, but if time runs at different rates in different places, which rate is the real rate? Is there a true time somewhere? And I think the answer is, that question does not have a clean answer, and the reason it does not have a clean answer is that the question assumes something about the nature of time that is not correct. There is no more a true rate of time than there is a true velocity. Velocity is relative. It only makes sense relative to something else. And in a similar way, the rate of time only makes sense locally in relation to your own reference frame and your own proper time, which is the time measured by a clock you carry with you. Proper time is real and meaningful. Universal time is a useful fiction that works in everyday life but does not reflect the deep structure of the universe. Let me also talk about something that connects gravity and time in a way that is more tangible and that a lot of people find surprising. The principle of equivalence. This is the idea that Einstein had that was, by his own account, the happiest thought of his life. He imagined a person in an elevator that is accelerating upward in deep space, far from any gravitational field. The person drops a ball and the ball falls to the floor of the elevator because the elevator is accelerating upward into the ball. From the person's perspective, the ball fell down, exactly as it would under gravity. Einstein said, "There is no experiment you can do inside a small sealed box that would distinguish between being in a gravitational field and being in an accelerating reference frame." Gravity and acceleration are locally equivalent. This is the equivalence principle, and it is the conceptual foundation of general relativity. Now here is the beautiful consequence. If you are in an accelerating rocket and you shine a light beam from the back of the rocket to the front, by the time the light reaches the front has accelerated away and the light arrives with a slightly lower frequency. It is redshifted. This is the Doppler effect applied to acceleration. But by the equivalence principle, this is equivalent to what happens in a gravitational field. A light beam climbing out of a gravitational well loses energy. It gets redshifted. Gravitational redshift. And this is directly connected to time dilation. If a light wave from deep in a gravitational well arrives at a higher point with lower frequency, it means that the clocks deep in the gravitational well are running slower. Fewer oscillations per unit of time means time is running more slowly down there. The redshift and the time dilation are the same phenomenon seen in two different ways. Beautiful. And we have measured gravitational redshift. Pound and Rebka did a famous experiment in 1959 at Harvard, shooting gamma rays up and down a tower and measuring the tiny shift in frequency due to the Earth's gravitational field over just about 22 meters of height. The shift was tiny, but they measured it and it agreed with Einstein's prediction. The geometry of space-time is real, and we can test it in a basement. One more thing I want to say about the arrow of time, because people often conflate two different things. The time dilation from gravity is about the rate at which time passes, but it does not say anything directly about why time has a direction, why we remember the past and not the future, why broken eggs do not reassemble themselves. That is a different question, connected to entropy and thermodynamics, and the second law, which says that entropy, the measure of disorder in a system, tends to increase. The past was a state of lower entropy, and the future is a state of higher entropy, and that asymmetry is what gives time its arrow. Gravity plays a role here too, in a subtle way, because in a universe with gravity, homogeneously distributed matter is actually a low entropy state. Gravity causes matter to clump together, to form stars and galaxies and black holes, and that process of gravitational clumping increases the complexity and structure of the universe even as the thermal entropy increases. The beginning of the universe was smooth and homogeneous, which is thermodynamically special, and the ultimate fate of the universe is probably cold and dark and at maximum entropy, but that is a story for another time. The thing I want you to take away is this. Gravity is not a force in the way Newton thought of it. It is the curvature of space-time, and time is a dimension of that space-time fabric, not a separate thing flowing uniformly in the background. Mass and energy curve space-time, and curved space-time changes the rate at which time flows, not metaphorically, literally. The tick of your clock, the rate of your aging, the frequency of light emitted by atoms near a massive object, these are all affected by the geometry of the space-time you inhabit. We have measured this with atomic clocks and gamma rays and GPS satellites and radio signals from spacecraft passing near the sun. The universe is telling us loudly and clearly through every precision measurement we make that time is not what we thought it was, and the most we can honestly say about why at the deepest level is that we are still working on it. And that working on it, that ongoing struggle to understand, is the most exciting thing in the world.